Hello guys, this is Journey Way, and this video is a record demo for the EE533-lab2. First, we need to build a synchronous 8-bit adder. Before build the 8-bit adder, we need to build a 1-bit adder first. This is a 1-bit adder, and we can use 8 1-bit adder to make a an 8-bit adder, and we need to make sure it is a synchronous 8-bit adder. So we need add 3 ED flip-flop, 2 in the input and 1 in the output. Let me test the 8-bit adder. Here is my test bench. I prepared the 3 set data to test it. The first set is 15 and 00. The second set is 7F and 80 with CIN is 1, and third set is FF and 01. Let me test it. Here you can see the result. Let me make it run longer. And we can see the result is actually correct. First, we can see in the first rise age, the data is in, and at the second rise age, the result is out. This 8-bit adder is actually can work normally. The second part of this lab is to build a 32-bit adder. 32-bit adder is made up with 4 8-bit adder, and to make it synchronous, we need add the flip-flops. Here is the synchronous 32-bit adder, and to test it, I also prepared 3 set of data. Let me try it out. And you can see the result is exactly right. Third part is that we need to make a 32-bit ALU with 5 functions. The first function is 32-bit adder, and the second function is 32-bit subjector, and the third function is to shift the bits, and we need to choose two other functions. I choose two functions instead. One is 2 plus 1, and the second is 2 minus 1. And this is my ALU circuit with 5 functional blocks: adder, subtractor, shifter, and plus 1 and minus 1. To make it an ALU, we need an opcode to choose the function, and to make it, I prepare these 32-bit marks, which made up with 32 821-bit 821 marks. Because it is a 32-bit 521 marks, so we need 32 1-bit 821 marks. Let's back to the LU, and I need to test it. First, I try to test it. The second function and the third function with the subtractor and the shifter. Let me try it out. Okay. We can see that the result is exactly right. 10 minus 6 is A, and shift makes 10 shift, it turn to be 20. Let me try the rest function. I need and release opcode. Minus 1 and plus 1. Save and begin. And we can see the result is exactly right. 11 minus 1 is 10 minus 1 is 11, and 10 plus 1 minus 1 is F. Yes. and we need to map it to see how many gates will we exactly used. Here we can see the number of flippers and the number of input LUTs. And the final part is to make the same LU with the Verilog language. Let me open the Verilog project. Here's my Verilog project. And we also have 5 functions: adder, subtractor, shifter, and -1 and +1. Here's my test bench. We try out for no test bench here, please. We try out 5 functions of this. And let's test it. Here is the result. And we can see A plus 1, A plus B is correct. A minus B is correct. Shifter is correct. -1, +1, they are all correct. Then let me test it. Let me test it the gate number. Here is the gate we used. We can exactly, but we can obviously see that the gate we use in the Verilog language is much less than the gate we use in the secret schematic. Um, this may be because the Verilog descriptions allow the syntactic tool to automatically optimize the logic. However, in the schematic version, um, the instantiates are all adders and flip-flops, resulting in higher gate usage. Okay, that's all of my demo of the lab2 in the EE533. Thank you guys.